Welcome back. In this video we're talking about trig integrals. So we're going to do two examples in this video. The first one is sine squared cosine cubed right here with some steps on the side, and then the second one we'll do with tangent and secant. Okay, so we'll start with sine and cosine. We do have some steps written on the side, but we're going to kind of talk about them as we go through this problem. And keep in mind you can pause this video at any time to actually write down all the details here. Okay, so the first thing I want to point out before we start is like notation. So for example, this cosine with the 3 right here and the x, this cosine cubed of x, it means the same thing as cosine of x cubed. So it's like cosine times cosine times cosine. We just kind of use this convention because it allows you to skip the parentheses, and you would need the parentheses here otherwise to make sure the cube doesn't end up on the x instead of the whole cosine. Okay, so what we're going to do is save either a sine or a cosine at the end of the integrand. And what the indicator is for which one to pick is which one has an odd exponent. So if they both have an odd exponent, you can just pick either one and keep going and you're good. And this one, the exponent on cosine is odd and sine is even, so I can see I want to split off one cosine. So I have 2 cosines left and then an extra one kind of saved at the end here. Now, the reason we're doing this is because they are each other's derivatives, so we know a creative u substitution is going to work. Really, all we're using is u substitution, just in a very specific way. So if we save this cosine of x dx at the end, we're kind of planning for that to be the du, which means that we are planning for, or we want, u to be sine of x. So whichever one you kind of save at the end, you're going to shoot for u equals the other one. Right? So if you save a cosine, you're going to sub in for sine. And if you save a sine, you'll be subbing in for cosine. Okay, so that would make this u squared. That'd be good. But then this right here, we have to do something with, right? Like that's kind of the awkward piece of this. Everything else would be ready to go. And that's where step 2 comes in. So step 2 is use the fundamental identity of trig, cosine squared plus sine squared equals 1, to turn the rest, what we mean is the rest of these cosines, into sines. All right, so if this is true, I can subtract sine squared from both sides, and I have cosine squared equals 1 minus sine squared. All right, so let's rewrite what we have before we do the substitution. So we have sine squared of x times 1 minus sine squared, that's instead of cosine squared, times cosine of x dx, and we are perfectly in business for a u substitution. So I'm going to do u equals sine of x, just like I planned. That would make du cosine of x dx. So a warning for other problems, in this one it doesn't matter, but in a problem where you're doing u equals cosine, its derivative is negative sine, so you'll have kind of an extra negative floating around when you put all the u's in. It doesn't make it harder, you just have to remember to keep track of it. All right, so what we have for the integral, sine squared becomes u squared times 1 minus u squared, and then cosine of x dx is exactly the du. Nice. Okay, so we still have to integrate this thing, and you may find it intimidating the way that it looks right now, but it's just because it's in a weird format. So this is where step 3 comes in. So we've done the u substitution, right? That part's good. And then I have this note here, expand the integrand. So what we'll do in this case is just distribute u squared into these parentheses. In higher power examples, right, so if this was like cosine to the 4th, this would have been squared, so you have a squared here, and you end up kind of foiling this and then distributing. So this can get kind of messy. We'll see more examples like that in class. But for now, all we've got to do is distribute. So I have u squared times 1 minus u squared times u squared. What I'm doing is adding the exponents to get that 4. All right, and now it's in perfect condition to just use the power rule twice for an antiderivative. So I have 1/3 u cubed, that's the u squared, minus 1/5 u to the 5th, that's my u to the 4th, and then plus c, and then my integral and my du are gone because I've actually integrated. Right, so that was pretty much the goal. The only thing left to do is just switch back into x, right? You don't want your answer to be in the wrong variable. So we'll go back to our substitution and say, okay, u was sine of x, so I'll just put sine of x in both of those spots, and that'll be it. So you can write this as sine of x cubed, or you can write it as sine cubed of x. They mean the same thing. I started writing it that way, so why don't I stick with it? They mean the same thing. And I'll stop here, and that is my final answer. I do want to point out before we continue, normally at this point I say like, oh, if you want to check your answer, just take your derivative and you wind up back at the original integrand. And that generally is true, and it's true here. The problem is what you'll get is not in the same format as your original integrand because there's so many trig identities that like turn them into each other. So don't get freaked out if you do check your answers sometimes. The magic of trig identities actually make it a little bit weird. So it'll look like it's different, but they're equal. All right, so let's move on to the second example. All right, so what I have here is not the correct steps yet. So what I've done is just rewritten the same steps as above, and we're going to kind of change them around so that they work for tangent and secant. So tangent and secant are sort of related in the way that sine and cosine are, in the big ways that matter, right? So they're involved in each other's derivatives, so the substitution kind of works. And they're connected by a trig identity like this, it's just not this one. Okay, so we want to think, what's tangent's derivative and what's secant's derivative? So we're not going to save a sine or a cosine. We're going to save either a secant squared or a secant tangent. Right, so not just one of them, but you're trying to save something for a du, and now it's going to be a tiny bit messier. So if we save a secant squared at the end, we would be doing u equals tangent, so you'd want to turn everybody into tangent in the next step. And if you saved secant tangent, you would expect u equals secant, oops, not secant squared, just regular secant. Let's completely get that out of there. So you would just be subbing in for secant in the next step, so you would want to turn everything into secants after that. All right, and so this identity is not what we want. Secant and tangent are related in a similar Pythagorean identity, and that is tangent squared plus 1 equals secant squared. That's how they're related. This actually comes right out of the same place that sine squared plus cosine squared equals 1 does, but don't worry about it. So this is what we'll always use, right there. All right, so, and then the same steps after that. You'll do a u substitution based on what you planned for, maybe some expanding, and then you convert back. Okay, so we no longer care which one has an odd exponent because we're not just pulling one out. So don't so much stress the exponents themselves. Just think, you know, if I took this out, could I get everything back in? Okay, so let me show you what I mean. What I'm going to do here is pull out a tangent, or sorry, a secant squared. So there's 4 of them, which means there's 2 left here, and then I save 2 of them at the end here. Normally what I do when I start these, I either write it down or at least kind of think ahead a few steps. And I first say, okay, if I pulled out a secant squared, would I have an even number of secants left to turn everything into tangent? You would need an even number to do it. At least for the rest of it to pan out, you would. Or if I pulled out a tangent secant, would I have even tangents left to turn back into secant? That probably didn't make a ton of sense, but we're going to keep going and it's going to make more sense, I swear. Okay, so we're going to kind of peek ahead here. So what I've done is going to pan out. This secant squared dx, I'm kind of saving this for the du. Secant squared is the derivative of tangent. So what I want, eventually, is for u to be tangent of x. So this would just be u squared, and we have that same kind of situation here where these remaining secants need to turn into tangents to pull this off. And that's, of course, where our identity comes in, the same way that it did in the first example. Here we have secant squared is tangent squared plus 1. So that's what I'm going to put in that spot. So this is why we would need an even number, right? So if I had like secant to the 4th, it would just be this stuff squared and so on. Okay, so we'll go one more step with that swapped in. And now we are ready to do, oops, there we go. Now we're ready to do our u substitution. This definitely looks kind of messy, but it's totally gonna work. So my u substitution is for tangent. That makes my du secant squared dx, okay, which is conveniently sitting right here. And this looks a lot like the example above. It's a little different, but it's really similar once we put in the u's. All right, so we would have u squared, that's tangent squared, times u squared plus 1. And then all of this is du. Almost identical to above. All right, so we've got that same extra step here where you might hesitate and be like, I don't know how to integrate this. But it should just be some kind of polynomial, so as long as you multiply everything out, the power rule will get you by here. So again, I'll distribute u squared before I integrate. Now I can use the power rule twice. And the very last thing I need to do is switch back into x. So here, everywhere I see u, which is these two spots here, I'll just write tangent x instead. We'll write it the fancy way in this one. And that is my final answer. That was fun.